We're continuing our chapter 6, which is about integrating more complicated types of figures created by solids of revolutions. And in this section, 6.4, we're looking at figures that we call shells. As we've seen, you can solve many challenging volume problems using the disk or washer method. There are, however, some volume problems that are difficult to solve with this method. For this reason, we extend our discussion of these problems to the shell method, which is similar to the disk and washer method. It's used to compute the volume of a solid of revolution, as you can see here. And this is when we have again, a region revolving around an X or Y axis, and you can see here it's not quite a flat disk or a washer in this case, and this is called a shell. So let R be the region bounded by the graph of f of x. You can see here on the graph on the left, and the lines x equals a and x equals b, where 0 is greater than or equal to a and a is less than b. And f of x is greater than or equal to 0 on that interval of a, b. When R is revolved around the y-axis, as you can see here in the diagram on the right, a solid is generated whose volume is computed with the slice and sum method like we've done before. So what we're going to do is we're going to divide the region, the interval AB, into n subintervals. This is exactly like we've been doing all along, so I'm not going to spend a lot of time on this, of length delta x equals b minus a over n, b minus a over n. This is the same thing we've been doing. And we identify an arbitrary point, x sub k star, on the kth interval for k equals 1, dot, 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 all the way up to n. Now observe the rectangle built on the k interval, that's here, on the diagram on the left, has a height of f of x sub k, the function value, and a width of delta x. So we have a rectangle's area. As it revolves around the y-axis, you can see here, it creates a cylinder similar to a disk that we've done in the past section. When the kth cylindrical shell is unwrapped, here's the shell. If we unwrap it, it approximates a thin rectangular slab. The approximate length of the slab is the circumference, the length of the rectangle, the length of the slab is the circumference of the circle because it was wrapped around into a circle. And so its length is 2 pi x sub k, okay? And because the radius is x sub k. The height of the slab is the height of the original rectangle f of x, and its thickness is delta x. So we can find the volume by multiplying the length times the height times the thickness, okay? Remember, the length is the circumference of the circle, the height is the functional value, and its thickness is that width of the piece that we're taking, delta x. So just as we've done in the past, what we're going to do is we're going to increase the number of shells. We're going to increase n into infinity. And you can see as we increase the number of shells, what we end up getting as n goes to infinity is this is our integral form of calculating the volume of a shell figure. And so we get the integral from a to b of the volume, which is 2 pi x f of x dx. Okay, this is exactly what we've been doing all along. And so this is just now in integral form, the integral from a to b of that volume to calculate the area. To calculate the volume. So before we move on to solving problems, let's look at a more generalized version of the integral for calculating a volume using a cylindrical shell. So in the diagrams that we use to kind of explain this, notice that we were just using one function, f of x, and then so we were just calculating the area under that curve all the way to the x-axis. But here we have a shell that's floating above the x-axis, and this will work in all cases. If there's only one function, then you would just use f of x. But of course, remember that if we're looking for the area r, then that height is going to be the difference, as you can see in the adjusted formula up here. The height will be the difference between f of x and g sub x. And so it doesn't change our formula a lot, but it allows us to use to calculate the volume for any of these figures, whether they are just below one figure to the x-axis and revolved, or if in this example, if it's between two different functions, the area between two different functions is then rotated around, okay? So this allows us to have a more general version of the formula, which will work for all figures. So if we go with a general formula, what we have for the volume by the shell method, if we let f and g be continuous functions, with f of x greater than or equal to g of x on the closed interval AB, and if R is the region bounded by the curves y equals f of x and y equals g of x between the lines x equals a and x equals b, then the volume of the solid generated when R is revolved around the y-axis is volume equals the integral from a to b of 2 pi x times the difference between f of x and g of x dx. Okay, so this is our integral that we'll use for the volume, calculating volume by the shell method. So let's look at our first example. Again, you have your paw prints here, so if possible, go ahead and pause and solve this problem. Let R be the region bounded by the graph f of x equals sine x squared, the x-axis, and the vertical line x equals the square root of pi over 2. Find the volume of the solid generated when R is revolved around the y-axis. If you don't feel comfortable solving this, at least hit pause and see if you can set up the original integral that you're going to need to solve. So a general formula is 2 pi x times the difference between f of x and g of x dx. In this problem, we do not have a g of x because it's between f of x and the x-axis, so we're just going to have 2 pi x f of x dx. If you'd like to see what this figure would look like, it's here. Again, if you haven't hit pause yet, hit pause and see if you can set up the original equation. That's pretty straightforward, okay? But here's this is going to be a cylindrical bowl that you can see that it's the curve of the sides of the bowl, the interior curves are that of the sine function. So if we set this up, 2 pi x times f of x, which is just sine of x squared, and we're going from 0, x equals 0, to x equals the square root of pi over 2. Now that we've set that up, see if you can pause and solve that integral. This is a good refresher from Calculus 1 to see if you can solve this integral, which is a little bit complicated. So hit pause and see if you can solve it. So we don't have a product rule for integrals, remember, but we had different strategies we can use. In this case, we're going to do a substitution. And if we set u equals x squared, notice that du, the derivative of u, equals 2x dx. And so we can get rid of the extra variable that's is one of the factors there. So if we do the substitution here, we get 2x dx. That takes care of the 2 and the x and the dx. And we get the sine of u because u is x squared. Remember the limits here are x values, so we have to convert them to u values. So if x equals 0, then u is also going to be equal to 0 because u is x squared or 0 squared. And if x equals the square root of pi squared, then u is going to be that squared, which is just going to be pi over 2. And so we get a much simpler integral to solve. We get pi, because we can pull the coefficient out in front, any constant multiplier, the integral from 0 to pi over 2 of the sine of u du. And of course, the integral of sine is negative cosine. And so we have pi times negative cosine evaluated from 0 to pi over 2. We plug in those values and we just get an answer of pi. So the volume of this figure is actually equal to pi. So let's try another example. This time we're going to do a shell about the x-axis. So let R be the region in the first quadrant bounded by the graph of y equals the square root of x minus 2 and the line y equals 2. Find the volume of the solid generated when R is revolved about the x-axis. Again, I'd like you to go ahead and try this on your own if you can. So we had some problems in the previous sections when we revolved around the x-axis versus the y and what the differences are there. And then you know the formula, the general formula here. So go ahead and try this problem if you can, and we'll work through it. Okay? So remember when we're revolving around the alternative axis, when we're revolving around x instead of y, we need to set up this formula a little bit different. Basically, we're changing the x's and y's in here. So wherever we have an x, we're going to have y, for example, 2 pi y. And of course, dy and not dx. And then the functions are going to be functions of y and not of x. So one of the first things that we have to do is to express our equation in terms of x equals instead of y equals. And so that's pretty simple. If we just solve the equation, we square both sides, and then we add 2, we get x equals y squared plus 2. At this point, it becomes a pretty simple integral. But again, see if you can set up the actual equation here with the limits of integration as well. So we know it's 2 pi y times f of y, which we've defined now, y squared plus 2 dy. And what are the values that it goes from what to what? Well, we can see here it's in the first quadrant, and it goes up to the line y equals 2. So we get the integral from 0 to 2 of 2 pi y times the quantity of y squared plus 2 dy. This is actually a quite simple integral to solve, excuse me. It's just a polynomial. If we move the constant 2 pi out in front, multiply the y through, distribute the y factor, we get 2 pi times the integral from 0 to 2 of y cubed plus 2y dy. And this is a simple power integral. It's not hard to solve, and the final answer is 16 pi. Here you can see the diagram, the two-dimensional diagram of the figures here in the top right. And then if you want to see the actual solid of revolution, this is a vision of it as well. Okay. So again, the key things here are to remember that our fundamental formula changes, that everything's an x becomes a y, so functions of x become functions of y, so we have to often solve equations for the other variable and use those in our integral. And then be mindful of the limits of integration here. What are the y values that indicate the radius, etc. Okay, or the circumference of the shell. So we've been at this a while now. It's a good idea after about 20 minutes of watching one of these videos, I know that they're not extremely exciting, but to go ahead and take a break or a timeout. I'm going to put some interesting things here in the middle of longer lectures. These are some great financial tips from Warren Buffett. If you don't know who Warren Buffett is, he's been often called the Sage of Omaha. One of the wealthiest men in the world, has given away half of his money to charity after he retires, or excuse me, after he passes away, and just has some really good common sense insight for your financial management, which we all know is probably one of the most important things to any of us. And if that is really important to you, then you really need to figure out investing strategies as soon as possible. And that doesn't just mean putting money into stocks, but you're already doing one of the biggest investments that you can right now, and that is investing in your education. It's one of the few sound investments that hardly ever goes wrong, unless you borrow too much money, which he probably says something about that. So take a break, go get a drink, take a step outside, do a little dance, do a TikTok, I don't know what you do, or just read these financial quotes. Excellent tips by Warren Buffett on earnings. Never depend on a single income. Make investment to create a second source. The sooner you get a second source of income that can support you, the stronger you'll be. There's also an old saying that says, once you've saved a full year's, not necessarily your salary, but a full year's spending, your whole psychological framework changes. And what that means is that if you know you have enough money to live on for a year, suddenly your choices about where you work and what you do for work become different decisions than when you have to pay the rent. On spending, if you buy things you do not need, soon you will have to sell things you do need. On savings, do not save what is left after spending, but spend what is left after saving. On taking risks, never test the depth of the river with both feet. On investment, do not put all your eggs in one basket. On expectations, honesty is a very expensive gift. Do not expect it from cheap people. And then his 10 or 11 things on investing. Risk comes from not knowing what you are doing. Be fearful when others are greedy, and greedy when others are fearful. You can't make a good deal with a bad person. Buy it thinking you will hold it forever. Investment is long-term. Money is about the long-term payoff. The most important investment is yourself. You get that with education. Price is what you pay. Value is what you get. Buy something you'd hold for 10 years. Think about that when you're buying a car. The second largest expense for most Americans is buying a car, especially for college graduates who tend to buy a new car every 4 or 5 years when they will last for more than 10. Don't put all your eggs in one basket. Spend what is left after saving. Again, he's saying it here, you should always put savings aside at the beginning of the month, not after you've paid all your bills. Don't rely on one income and never lose money. Let's look at a little bit tougher problem here. Example 3, the volume of a drilled spear. A cylindrical hole with a radius r is drilled through the center of a sphere with radius a. So the sphere has a radius a. The hole through the center, a cylinder, has a radius r, where 0 is less than or equal to r is less than or equal to a. What is the volume of the remaining material? So basically we have a sphere with a hole through it. And so sometimes it's really important to kind of visualize these, and if you don't have a diagram or a graph, you have to build one. So a sphere is just the rotation of a circle, and remember that the equation of a circle is x squared plus y squared equals the radius squared, and that is a circle centered at the origin. So if we look at this diagram here, the sphere is centered at the origin. The radius of the sphere is a, as we can see here. So the equation of the line is x squared plus y squared equals, in this case, a squared. And so if we want to determine the equation in terms of y equals, or f of x, then we'd have y squared equals a squared minus x squared, and of course y would then equal the square root of that. So since we are not just revolving, R is not just the region between this f of x positive version and the x-axis, we can think of the graph below the x-axis as a different function, g of x, and it has the same equation, but it's the negative square root. And that's what takes care of it being a full circle, that we have positive square roots above x, and then, of course, negative square roots below x. So we can see now that we can use this in our general formula, f of x minus g of x. Well, if we have the square root of a squared minus x squared minus the negative of that same value, then what we're going to get is 2 of those as far as the value of f of x and g of x. And in this case, we are integrating from the values of r to a. That's the r interval. We're going from r to a, because again, what we're trying to figure out is how much material is left after we drilled this hole through the center of the sphere with a radius r. So the material starts at r and goes out to the x value of a. Sometimes these can seem confusing for students when we don't have when we have what seems like many variables in here. But remember, a is a constant, and so is r. So in this case, if we do a substitution, u equals a squared minus x squared. Since a is a constant, our du equals negative 2x, and we can greatly simplify the integral into negative 2 pi, integrated from a squared minus r squared to 0. And again, if u equals a squared minus x squared, and the x value is r, then we're going to plug that in and get a squared minus r squared. And here, if the value is a and u equals a squared minus x squared, if x is a, then we get a squared minus x squared, so we get 0 as the upper limit. And then, of course, the square root of u du. This is not a very difficult integral to solve. And notice that when we plug in 0 into our solved integral, everything goes away. So we get 0 minus the negative, which is just the positive. And so we simply get that value of a squared minus r squared plugged into this equation. So sometimes it's really difficult to tell. It can be difficult to tell if we're on the right track, or if we've done some algebra wrong, or we dropped a variable here. So conceptual checks are really a good idea here. If you might recall that the volume of a sphere is equal to 4/3 pi radius cubed. So if we make the radius of the hole 0, like if there is no hole, notice what happens. We get 4/3 pi. A squared, taking the square root of that is a raised to the 3rd power, we get 4/3 pi r cubed. And so we can see we get the actual volume of a solid sphere if we make that hole radius 0 or no hole at all. And so that's a way to kind of conceptually check our work as well, to make sure that we're on the right track. So let's look at example 4 now, and this is when we're going to be revolving around other lines, not just the x or y axis. These can be a little bit more complicated, and we're going to use both the shell method and also the disk method to show you that we can use typically either method depending upon which axis we're revolving around. So let's look at example 4. Let R be the region bounded by the curve y equals the square root of x, the line y equals 1, and the y-axis. Part A, use the shell method to find the volume of the solid generated when R is revolved around the line x equals -1/2. So our line of revolution is actually x equals -1/2. It's the vertical line, a half an inch, or excuse me, a unit to the left of our left boundary here. So remember that our general formula for the shell method is the length of the rectangular slab when that circle is unfolded or unrolled. So this is the actual circumference, 2 pi times the radius. Our radius of the circle is going to be whatever our x value is for f of x and g of x, plus that 1/2, because we're no longer revolving around y, so the x value would just be, this is the radius if we were revolving around the y-axis, but since we're revolving around x equals -1/2, we're going to have to add 1/2 to x because, you know, for example, if we're doing this, this integral of, this specific shell where our x value is somewhere along here, then the x value equals x plus the 1/2. It'll be easier to see. So here we get 2 pi. The radius is whatever our x we're using at that point, plus 1/2, because we have to go another unit of 1/2. I think it's easier to see here. Again, if we were revolving around y, then just the x value would be the radius of the circle that we're calculating each time and unfolding, if you will. And then the height, of course, is f of x minus g of x, and then the thickness is the d of x. But since, again, we're revolving around x equals -1/2, instead of 2 pi x, we have 2 pi x plus 1/2. So you need to really be able to understand conceptually how to find the volume using the shell method or the disk method, and then visualize what's happening in the example, okay? And then, of course, the height of that rectangular slab is easier to see, excuse me, from the two-dimensional figure, which of course is f of x equals 1, and g of x equals the square root of x, so it's f of x minus g of x, which we see there, 1 minus the square root of x. The setup of these problems is really the key. It's being able to visualize them and then understand the formulas again conceptually, and then plug in the equations that are appropriate for each problem. If we plug this in, we get, if we multiply this out and clean it up before we integrate, we get 2 pi times the integral from 0 to 1 of the quantity of x minus x to the 3/2 power plus 1/2 minus x to the 1/2 over 2. And all of this is differentiated with respect to x dx. Taking the integral, we get 2 pi times 1/2 x squared minus 2/5 x to the 5/2 plus 1/2 x minus 1/3 x to the 3/2, evaluated between the values of 0 and 1. Plugging those in, we get a final answer for the volume of 8 pi over 15. An interesting thing here is, and you can probably see that, this actually looks like a disk. And we could use the disk method to solve this as well, okay? And we're going to look at how to figure out which method to use each time, or when methods are appropriate, and how the shell method compares with the disc and washer method. And you can see here, it looks like a little washer in there. Okay. Now let's look at part B for this problem. We have the same curve, y equals the square root of x, the line y equals 1, and the y-axis for the region, for the boundaries of the region. Okay. Part B says to use the disk washer method to find the volume of the solid generated when R is revolved around the line y equals 1. Notice that is actually one of the boundaries of our region. And so going back to the dishwasher method, remember that what we're doing now, instead of with the shell method, we've kind of, you unroll the circle, and the circumference is the length of the rectangle. So we're using length times width times thickness. Here, with the disc and the washer method, remember, we have a circle. So we're doing the area of a circle times its thickness, dx, okay, for its volume. So the area of a circle is pi r squared. So the volume would be pi r squared times dx. It should say dx in there too, okay? So when we look at this function, we can see that when we're revolving around y equals 1, the radius is going to be from that center point where we're revolving out to this other function, the square root of x. So we're going to get the volume equals the integral from 0 to 1 of pi times the radius square, and the radius is going to be 1 minus the square root of x. Each disk is going to be that's going to be the radius of each disk, because the center is at y equals 1 where it's revolving around, and then the thickness of each disk is dx. You might be able to see it easier here. And then once we have this is a pretty straightforward integral to solve. We pull the pi outside. We go ahead and FOIL the 1 minus the square root of x squared. Apply the integrate, and then apply the limits, and we get for the final value pi over 6. Again, we could use shells for this, and we could have used the disk method for the other problem. So we're going to look at that now. So this leads us to a question about which method do we use. After working with slices, discs, washers, and shells, you might feel a little bit overwhelmed about how do I choose a method and which method is best. But first notice that the disc method is just a special case of the washer method. So when we're doing solids of revolution, the choice is between the washer method and the shell method. Okay? In principle, you can use either method, but in practice, usually one method will produce an easier integration. And so that's what we're shooting for, is to figure out which method will give us a formula that's easier to integrate. So let's look at how we can use either one. If we're talking about integrating with respect to x, notice that we'll use the disc and washer method when the figure is being revolved around the x-axis. And that is that discs and washers are perpendicular to the x-axis. That's when we would integrate with respect to x. We could also use the shell method if it's revolving around the y-axis, and where the shells are parallel to the y-axis. And notice that both of these are integrating with respect to x. So what's happening is that the disc and washer method revolves around the axis or a line that's equivalent with what you're differentiating with respect to. And you'll see that in the next slide. Here, where we're differentiating with respect to y, again, the disc and washer method is revolving around the variable which we're integrating with respect to, in this case, y. So we would use we would integrate with respect to y using the disk and washer method if the figure is revolving around the y-axis or around the vertical line. And we would use the shell method for figures revolving around the x-axis, as the shells are parallel to the x-axis. And so I'm going to look at our last example in this chapter, and it'll illustrate how we'd get the same answer with both, but one is a lot easier to integrate. So let's look at our last example, determining volume by different methods. Let R be the region bounded by the graphs f of x equals 2x minus x squared and g of x equals x on the interval 0, 1. Use the washer method and the shell method to find the volume of the solid formed when R is revolved around the x-axis. Well, the first thing we have to do is figure out where the points of intersection are so that we can figure out how the figure is bounded. We can graph it, or we can solve the equation f of x equals g of x. And when we do this, we see the curves intersect at the origin 0, 0, and at the point 1, 1, which you can see here. And again, this is good it's a good idea to visualize to see what's going around, to see what's happening with the figure and where it's revolving around. So if we use the washer method, notice that the radius is going to be the outer function, which is f of x, minus the inner function. So it's pi f of x minus g of x, which would be the radius squared, dx. And so here we have the washer method, and it's a pretty straightforward, again, pi r squared. Of course, with the washer, you're subtracting out the area of the whole, pi r squared of the whole, which is the smaller version. Pretty straightforward to solve. I'm not going to walk through this. You get the integral of from 0 to 1 of pi times the quantity of 2x minus x squared squared, that's f of x, the outer radius, minus x squared, which is the inner radius, dx. And when you solve this, you get pi over 5. Now, if we are using the shell method, then we are looking for the circumference of the circle when it revolves around, and so we're measuring that from the y-axis. So so we're going to have to rewrite each of the functions in terms of f of y instead of f of x. And so again, it's 2 pi. The y value is the circumference of the circle as we revolve around the x. And then you have the shell height, which would be this formula minus, because we're going from the y-axis, g of x minus f of x. But of course we have to define each of these in terms of their variable, the other variable y. So here we get just x equals y. That's our outer function, and then our inner function is a little more involved, as you see here. Okay. The thing is that this will give you the same answer, but the second integral is a lot more complicated. Not a lot, but it is more difficult to solve and would take a bit more time. And so while these both will give you the same answer, what we have here is a much easier integral to solve. And so that's why both methods are there. And you kind of figure out, look at the integrals and see which method you want to use.